Given a query graph Q and a vertex labeled graph G, the problem of subgraph isomorphism is to find a one-to-one mapping from every vertex in Q to a vertex in G with the same label. Similarly, each edge in Q is mapped to an edge in G. Such graph querying is often restrictive. In the example here, no match is found for subgraph isomorphism. Bounded one-to-one P-homomorphism, referred to as BPH, extends the subgraph isomorphism concepts by allowing mapping of edges from Q to bounded paths to G. A bounded path is defined by a minimum and a maximum path length as shown here. For instance, the bounded path of edge, APAF1, bid, in Q has minimum and maximum path lengths of 1 and 2, respectively. In the example here, BPH finds a match compared to subgraph isomorphism which returns no match. The match in the BPH results is due to the allowance of edge to bounded path mapping. This allows mapping of the edge, APAF1, bid, in Q to the path APAF1, BCL2L1, bid in G. Similarly, the edge, APAF1, BCL2, in Q to the path APAF1, BCL2L1, BCL2 in G. Other edges in Q are mapped in similar way to their corresponding paths in G. Observe that subgraph isomorphism is a special instance of BPH when the bounded paths in G correspond to edges. In this video, we present BOOMER, a tool for blending visual BPH and exact subgraph queries on large networks. The key features are visual formulation, blending visual query formulation and query processing, deferred execution to handle challenge of edge-to-path matching and small region-based visualization. We shall demonstrate how to formulate BPH and exact subgraph queries and analyze their results using real-world networks. In the first example, Bob, a biologist, uses a BPH query to find out if C. elegans organism is suitable for studying apoptosis in human. The BPH query vertices in the red box are human genes that are homolog to C. elegans genes related to apoptosis. Bob is interested if these human genes interact in the same way as the corresponding C. elegans genes. First, Bob selects a database called Human PPI, which is a protein-protein interaction network where the nodes are proteins and edges are the interaction between proteins. Then, he loads the index of this network and initializes the query panel by clicking the Add Query button. Next, Bob constructs the BPH query by using the labels in the Human PPI database. He chooses the required labels from the list by browsing, selecting, and performing a drag and drop action. Edges are then added between the vertices. The BOOMER interface allows Bob to easily configure the minimum and maximum path length of each edge. Here, the minimum and maximum path length of edge, bid, BCL2, is set to 2 and 3, respectively. In BOOMER, edge processing occurs while the query is being formulated. When an edge is processed, its color changes from black to blue and the query processing plan panel is updated with relevant edge information. BOOMER allows query modifications such as node and edge deletion and modification of edge bounds. Here, we illustrate edge bound modification using a left mouse click. The upper edge bound is modified from 4 to 3. Edge information is displayed using a right mouse click. Once Bob completes the BPH query, he clicks the Run button to request for the query results. The number of partial matched vertex sets is shown and Bob can view the results by clicking on the View Results button. Since it is cognitively challenging to visualize results subgraphs on a large data graph, BOOMER deploys a small region-based visualization scheme where it iteratively shows a color-coded small subgraph of the underlying data graph that satisfies the user-specified edge-bound constraints. In particular, BOOMER displays the result in a separate panel where the orange-colored vertices correspond to vertices in the BPH query. The remaining vertices in the results which are colored in blue are the intermediate vertices whose path length satisfy the edge bound of the BPH query. The results dialog box shows information of which BPH query vertex is matched to which data graph vertex. BOOMER also displays details of the cap construction time. In particular, BOOMER identifies all result subgraphs that satisfy the BPH query edge-bound constraints. In this result, vertices APAF1 and BID are connected via the intermediate vertex BCL2L1. Similarly, vertices APAF1 and BCL2 are connected via BCL2L1. Hence, BCL2L1 is an interesting gene that may be used for regulating pathway signaling of APAF1, BID and BCL2. The previous and next button in the result visualization panel is used to iterate through all the results for current selected partial matched vertex set. Iterating through the results allow users to view all the possible alternatives paths between each pair of query vertices that satisfy the edge-bound constraints. In the next example, we explore the use of Wordnet database for sentence clustering using parts of speech syntax, which can be applied to identify spoken language. Wordnet provides 5 parts of speech categorization, namely, noun, verb, adverb, adjective and adjective satellites. Here, we construct a parts of speech graph consisting of adjective, noun, and adverb. Observe that the processing of the first edge is delayed as the color of the edges remain black. BOOMER chooses instead to process the next constructed edge, NR. This is due to the high estimated edge processing time as there is a large number of match for vertex N. BOOMER implements a defer to idle strategy for edge processing. After processing of the third edge, AR, the number of matches vertices is vastly reduced and processing of the first edge, AN, is deemed feasible. Hence, BOOMER processes it. Observe that the query processing plan panel is dynamically updated as query blending occurs. Users can harness the BPH query results to learn lexical concepts. For instance, partial matched vertex set 72 and 75 yield graphical results with the same topology. The vertices in the two graphs are identical except the match for vertex N. Hence, these two noun singing voice and low pitch are likely to be related and can be grouped together to describe a concept. In the next example, another scientist Jane is interested to find out if close relationships exist between breast cancer, colorectal cancer, and endometrial cancer. An application of this knowledge is in helping to identify common drugs that may be used for these 3 cancers. Similar to previous example, Jane first loads a database called Human Cancer which contains the PPI network of human genes implicated in cancer. Then Jane proceeds to construct the query using the labels in the Human Cancer database. The end query is a subgraph isomorphism search of a triangle connecting breast cancer, endometrial cancer, and colorectal cancer. In this example, BOOMER returns 9 partial matched vertices set. Note that visualization of exact subgraph query results contain the partial one-hop neighborhood of the subgraph query vertices to give additional contextual information of the current result. BOOMER displays a maximum of 5 one-hop neighbors per query vertex to avoid cluttering up the display. Additional one-hop neighbors can be retrieved on demand. These vertices and their edges are colored in gray. Jane can easily browse through the partial matched vertices sets by using either the drop-down selection list or the left and right buttons. We observe that there are multiple gene sets satisfying this particular query. For the current gene set, the gene implicated in breast cancer and colorectal cancer are related to ovarian cancer as well. Hence, drug development focusing on this gene set may not only be beneficial for breast, colorectal and endometrial cancers, but for ovarian cancer as well. In conclusion, BOOMER contains various innovative and user-friendly features for supporting both BPH and exact subgraph queries.